All right, picking up where we left off, we're doing heaps today. So go ahead, there should be a poll everywhere live. Go ahead, is this a valid min heap or no? Discuss. Shout out to our wonderful TAs. If you have questions, look at these wonderful TAs. Raise your hands, TAs. Shout out to these wonderful TAs. If you have any questions, ask the TAs questions. They're here for you. All right, let's chat about it as a group. If you haven't, fill out that poll everywhere. Okay, so before we dive in, does anyone want to remind me, there are 3 invariants that we must pass in order to be a valid binary min heap. The first one is binary. Every node has to have at most 2 children. Then we have the heap invariant. Can anyone remind me what the heap invariant means? It's about the order of the values. What has to be true about the order of the values to be a valid heap? It's kind of like the equivalent of the binary search property, but it's not quite as strict. Yes, please.
Is it where the parent node has to be less than or equal to the 2 children nodes?
Exactly. So for every child, I must be greater than or equal to my parent. So the smallest value has to be at the overall root, and then every value underneath has to be progressively larger. It doesn't matter left or right. We just care that the parent node is smaller than the child nodes. Okay, and then there is a third invariant for a heap. It's about the structure. It's about how we fill up the tree that forces it to be that nice bushy, short tree that gives us that fast runtime. Can anyone remind me what has to be true about the structure of a heap for it to be valid? Yeah, sure.
The way it's filled, it has to be filled top to bottom, left to right.
Yes, I love that. Top to bottom, left to right. In other words, it needs to be complete, but that's exactly what complete means. It means that as we fill up the tree, we must completely fill up each row from left to right before we start a new row. So otherwise also known as no gaps. So let's talk about this first heap on the far left, the one with the overall root 8. Thumbs up, valid. Thumbs down, invalid. What do we think? I see mostly thumbs up. I agree. That is a valid heap. 8 is smaller than 9 and 10, and we have no gaps. Okay, let's talk about the middle heap, the one with the overall root 2. Thumbs up, valid. Thumbs down, invalid. Oh, we were much more confident about this one. Okay, I agree. It is invalid. Does anyone want to raise their hand and tell me why is this invalid? Yeah, sure. Node 5 has a child that's less than it, which is 4. Yeah, 5 breaks the heap invariant, so the ordering is off. So that's invalid. But if it wasn't for that 5 and that 4, let's say we swapped them in order, would this then be a valid heap? Is this otherwise a complete tree? Yes. So the structure of the middle one, totally fine. It's the ordering, the heap invariant that's broken there. And then we have another one to the far right, the one with the overall root. Thumbs up, valid. Thumbs down, invalid. Yes, I agree with the thumbs down. Feels almost Roman in a way. Does anyone want to raise their hand and tell me one of maybe multiple reasons why this one is invalid? What's one reason this could be invalid? Yes?
It's not level complete, like you're on the first level when your level isn't filled up.
Yes, it's not level complete. I like that way of thinking about it too. It's got gaps, so we can see there's actually a couple gaps here. The node 3 has a gap to the right, but then there's a whole nother level started after that. So that 22 shouldn't have been placed on the third row if there was still a gap to the right of 3. Same thing for the left child of 4. There should not have been anything to the right placed if there was still that gap there. Are there any other problems with that one? I can't remember if I put anything else in there. No, we're okay? Okay, now I'm going to see. Yes, okay. So there we go. There are issues. Does anyone have any questions about this warm-up? Okay, great. Okay, so you have a midterm on Friday. Hopefully that is not a surprise. Does anyone have any remaining administrative questions about the midterm? There is the TA-led midterm review later this evening. It's in Smith, the big one, this big Smith room, right? Yeah, I want to say like 150. You go downstairs and to the right, whatever that is, right? Yes, any questions at all administratively at this point? Great. So I'm going to see all of you on Friday, and we're all going to be relaxed and rested. At least rested, please. I promise. I know you want to cram late, but it doesn't help. I know. Okay. Then let's get into it for the day. So where we left off on Zoom on Monday was implementing add to a heap. So here I have a heap, and this is a valid heap as it currently stands. It is complete. The only gaps are to the right of the leftmost bottom value. And what we want to do in order to add things to a heap is, remember, unlike the AVL, we are going to first maintain the structure invariant and then fix the order invariant. In the AVL, we were sort of maintaining the order invariant, the binary search property, and then we were rotating to fix the structure. And that's partially because binary search is stricter than heap, because we have to go left and right. There's really only like one valid place for something to be in an AVL tree, and then we rotate to make it work. This is opposite. The structure invariant is actually the stricter one, so we maintain the structure first, and then we percolate, which is going to be us swapping values. We are mutating nodes in this particular case in order to get back to that heap ordering property. So this is where I'm going to add any value to this heap. It doesn't matter what the value is. I'm going to first place it into the heap. So let's say I place the value 3. I have maintained the structure invariant, but now I have broken the heap invariant, and what I'm going to do is I'm going to percolate up. I'm going to ask 3, swap with your parent if you are smaller than your parent. 3 is smaller than 8, so we swap, and then we ask again, is 3 smaller than 4? Yep, so we're going to swap again. Is 3 smaller than 2? No. So we just we found our place where we're going to hang out. And now we have maintained both the structure and the heap structure, heap invariant. Any questions? I know I did that very briefly at the very end of lecture on Monday. Great. So this gives us then a worst case runtime very similar to remove min, where it is a logarithmic runtime, and that is because the height of the tree is log n, and the worst case is if I have to go all the way from the last row all the way up to the overall root. So the worst case in any of these heap interactions is that I have to travel one entire height of the tree. In this case, we didn't actually have to go all the way up to the overall root. And if you think about it, it's actually, depending on the order, somewhat statistically unlikely that you always have to go all the way up. But whenever I ask you for the runtime, I'm asking for the worst case scenario. And the worst case is if the new value you add into the heap turns out to be the new minimum value and has to go up every single level through percolations. Why don't you practice? Okay, so go ahead and construct a minimum binary heap by adding the following values in this order. Go ahead, take a few minutes, talk to those around you. I'm sure the TAs are down to help you. Go ahead, take say 4 minutes to do this. All right, let's chat about it. so first we want to place 5. 5 becomes our overall root. Now we want to place the value 10. Who can raise their hand and tell me, where do I place 10? Yes, please. To the left of 5. Absolutely. Remember, we're going to start a new row because this row right now is considered complete. And we always fill from left to right. Now, we've placed 10. We're always going to place for structure first. Do we need to do anything else? Oh, convenient. 10 is greater than 5, so we're going to leave it there. Okay, now it is time to place the 15. Can anyone raise their hand? Where does the 15 go when I place this? Yes, please. To the right of 5. Absolutely. That's the next available spot. And again, 15 is greater than 5. Looking good. It's already there. We don't need to do anything else. We've maintained both the structure and the heap invariant. Now it's time to place 20. Where does 20 go? Anyone want to raise their hand? I am not trying to trick you. These are hopefully, yes, over here. To the left of 10. Again, we're starting a new row. We're filling from the left to the right. So 20 goes there. Do we need to do anything else to fix this? No, I agree. 20 is greater than 10. So helpful. Okay, so now it's time to place 7. Where does 7 go? Anyone? Yes, please. It'll start at the right of 10. Absolutely. That's exactly where it goes. But we've maintained our structure, and now it is time to percolate. And just like I think you have indicated, it is going to percolate, so we are going to swap it with the 10. But then we've gotten to here, and do we need to percolate anymore? We only have to do 1 percolation for 7 to come to its final resting place. All right, now we need to place the 2. Where does 2 initially get placed? Where's 2 going to go in this so far? Yes, please. To the left of 15. Absolutely. There it goes. And then is it going to do, I see your wonderful hand gestures. Is it going to percolate? Yes, I agree. I love those. So it's going to percolate with the 15. Is it done? Does it keep going? It's going to do 1 more. Agreed. Aha. I think this is its final form. Any questions? I'd be like, Casey, we get it. We don't usually do this much practice in lecture. Once, because we have the time to do it with these structures, which is great. But also because guess what P3 is? Implementing a heap. Huzzah. Okay, so let's talk a little bit about runtimes, and then I'm going to spend the rest of lecture talking about how you actually will implement these in P3. So min heap runtimes, remove min. You remove the overall root. You find the last node in the tree and swap it to the top level. And then you percolate down to fix the heap invariant. So removing the root node, the overall root, that's a constant time. We have a pointer right to it, so that's just an O of 1. Percolating down to fix the heap invariant, that's a logarithmic runtime. Just got to travel the height of the tree. But this middle piece here, find last node in tree and swap to top level, ooh, that feels a little, do I have to like search through the tree, or do I need to keep a separate pointer? Like, what's going on there? Yes, if you were doing this with nodes that all connected to each other, you might have a pointer, or maybe you're doing like a tree traversal to find everything, which could possibly incur you a linear runtime. But I'm going to show you how to do this in a way that will actually be constant runtime. Ooh. Same thing with add, inserting a new node into the next available spot. How do I know where the new next available spot is? Do I maintain a pointer? Do I have to search through the tree? I have a trick for you. But we know the percolate up. Anytime we're percolating up or percolating down, that's always going to be a worst case runtime of logarithmic run. Great. Now we have officially finished the slides for Monday. Here's the secret of how we actually implement a heap. We don't actually make nodes that point to each other. Instead, we have an array that stores values in a way that represents an imaginary heap. And so you will see when you come to us in your P3 questions, we may draw this type of thing out for you regularly because the tree structure still exists, But it's not going to be stored in nodes. It's going to be stored in an array. And the way that you store things in the array is, let's say we have a heap that looks like this, where A is the overall root, and then it's got B to its left and C to its right. Well, the way you would store that in an array is A is stored at index 0, and B is stored at index 1, and C is stored at index 2, and so on and so forth. And so actually you can see we store the values in the array according to the same order in which we fill up the heap, top, down, left, right. So now, remember how I kept saying we're mutating nodes and we're swapping things around? Instead of mutating nodes, you're not changing fields within a node, you're just swapping values in an array. Much easier to do. But what you do need to do then is every time you're trying to travel around your tree is you're going to have to use a little bit of algebra to navigate within the indices of the array. In fact, here's some of that algebra for you. So peak min, now we just look at whatever the heck is stored at index 0. Great. We maintain the constant time lookup, just whatever's at index 0. How do we find the last node? Well, now, because we know we're going to be filling it up from top down, left to right, the last node is whatever is at array at index size. Because, of course, we're going to have an array with some larger capacity than we filled up. But in this particular case, we've got how many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We've got 12 nodes, if I did a quick count there, which makes sense because L is stored at index 11, which is size minus 1. So if we wanted to remove min, we return what's at index 0, and then we swap whatever's at index 11 with whatever's at index 0, which is also really convenient because then we just decrement size, and k becomes the new last item. How do we find the next open space? Well, the next open space is just at array at index size. And this is all nice and clean because of zero-based indexing, right? So in this case, there's 12 items already stored in here because of zero-based indexing. The last thing is at index 11. So if I wanted to do add, the next thing I would add has to go at index 12. I don't have to do some search through the nodes. I don't have to do any traversals. Constant time. Right there. This is the stuff that might be the least fun, depending on your definitions. But if you are trying to navigate to a node's left child, any given node's left child is 2 times my index plus 1. So if I wanted to find A's left child, 2 times 0 is 0, plus 1 is, oh, there it is, index 1. If I wanted to find A's right child, it's 2 times 0 is what? Plus 2 is what? Aha. Okay, let's do something else. Okay, let's say we want to find E's left child. We come in here. We know E is at index 4. 2 times 4 is what? 8 plus 1 is what? Boom, there's the J. And you can imagine 2 times 8 plus 2 is 10, which is the K. And you can then algebra reverse engineer that so you can go from child back up to parent. Because also remember when we were doing those percolations, we were constantly asking ourselves, am I greater than or smaller than my parent? And usually children don't know about their parents. I was just kind of blasting through that, somewhat expecting somebody to be like, Casey, how do you know? This is how we know. We can reverse engineer just by navigating through algebra within the index of the array. Questions? This is what I'm going to ask you to implement. This is the big secret. I really want to make sure that you're comfortable because I'm going to ask you to literally create a heap in this manner. Yes, please.
For finding the parent, is it the same formula for both left and right children?
Yes, great question. So finding the parent, is it the same for both left and right children? It is, thanks to integer division. One of the few times that integer division actually makes sense because we just drop any of the decimal points. This one formula works the same regardless if you're on the left or right child. Any other questions? No, because this all seems plenty fine when we're here in lecture together in the light of day, and then see how you feel when you're trying to turn this in at 10:30 p.m. on Thursday next week. I'll see you on the ed boards. Okay, cool. So let's talk about some of the runtimes now that we're using an array. So remember, previously we sort of had these logarithmic runtimes based on traveling within the tree. We have matched the asymptotic worst case scenario of AVL because of our invariance. But we are actually doing better because, remember that thing about contiguous memory? How arrays just function faster because it's faster to find the place in memory of the index of an array as opposed to finding the location in memory of where the pointer from the node goes. So array-based heaps turn out to be one of the most efficient structures, and certainly one of the most efficient structures to find the minimum or maximum value. Spoiler alert, we'll even use them as a sorting algorithm. They're in fact one of the most efficient sorting algorithms as well. Okay, great. Great, yes. And a heap is so much simpler to implement than an AVL, which is why we ask you to implement a heap and not an AVL. Yes, great. You can read this. This is me just discussing things for you. But let's talk about Project 3. That's what people care about. So Project 3, you're going to build a heap. You're also, if you have not been suffering the pains, is going to be a collection of collections, just like your chained hash map is. You've got an array of items, things like that. You're going to directly apply all the invariants. Make sure that every single method you write satisfies the invariants by the end of the completion of that method. You are going to write add, remove, peek, min. You're also going to add something called change priority. That is a method where you are going to add functionality that does not normally exist. The heap is normally implementing a priority queue. A priority queue or a queue or a stack typically does not allow you to access the values in the middle in any way. Those structures are traditionally only interact with the front, maybe the back kind of situations. But we're going to ask you to go a little bit further. You're going to implement something called change priority, which means dive somewhere into the heap, alter the priority of that value, and then it will need to find a new location in the heap. So you will need an extra data structure for change priority. It will be something to allow you to find where something is within the heap. This is actually a really common thing in data structures, especially when we get into the graph section after this week, that you have a structure that holds everything, and then you have a separate structure that helps you find things within the thing that's holding everything. Let's see, what else can I say without giving too much away? I'll let you read this. Great. I know this probably doesn't make a lot of sense. We'll post P3 tomorrow, and let's be real, you're all going to focus on the midterm. You're not going to get into it until later. I'm going to be real with you. P3, especially after P2, a little bit gentler of an experience, if you will. Cool. Okay. Okay, let's talk about priority queues a little bit more. So let's see. This is fine. Great. Oh, let's talk about build heap. Yep. So, so far we've sort of talked about building up the heap one little bit by one little bit, and it's already pretty efficient, right? So we could, like we did in our last example, add things in individually one item by one item. Can anyone imagine the best case scenario for the order in which to add elements into the heap? What is going to cause the fewest percolations for the order of elements we add into the heap? Remember in that last example how 5 was the first thing we added, and that was a pretty small number, and the numbers after it were kind of larger and they caused fewer percolations? What's the best case scenario ordering of items. Yeah, in the back. Absolutely. Sequential increasing numbers. So if we want a min heap, its best performance is adding sequentially increasing numbers. So like 1, 2, 3, 4, 5, something like that. Okay? What's the worst case scenario of items? What's the worst case order I could add items in then? Yeah, sure. Greatest to least. Absolutely. Because then I have to do a ton of percolations, right? If I add the largest number first and then the next thing I add is smaller than it, that's going to cause a percolation. And if every subsequent number is smaller, constant percolations, right? Now, we don't get to control the state of our data, and this is a true best case versus worst case scenario. That's not based on n, right? Best case scenario, you get added in ascending order. Worst case scenario, descending order. But knowing that this could happen, can we be even more clever about how we fill up a heap at the beginning when we create something? So there is a method called build heap, where instead of adding elements one at a time, we take a collection of elements, we add them all at once, and then we fix the structure of the heap in one sort of collective move. That's called build elements. If we didn't do them all together, we just called insert n times, we would get an n log n runtime in a worst case scenario. Because the worst case is log n, we do it n times n log n. Great. This is also when I used to make you do proofs. You can read that if you are so inclined. But welcome to Floyd's build heap algorithm. We are going to build a tree with the values 12, 5, 11, 3, blah, 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 so on and so forth. You could go through and just call insert individually on all of those. But what Floyd hypothesized is, what if instead we just first add all of the values into the array all at once? We're not doing them sequentially. We're doing them all together. That then creates a tree that looks like this. So it's actually stored in the array, remember, but the heap lives on in our minds, in our hearts, in this imaginary context. So first we add everything starting at index 0 all the way to the back of the array. Now what might be unintuitive is instead of saying, oh, well, like there's probably a lot of values down at the bottom that need to get to the top, let's call percolate up on them. No, we're actually going to go through the array level by level, calling percolate down. So what's going to happen is we're going to start at the back of the array. We're going to start at 6, and we're going to call percolate down. And you're like, but Casey, there's nowhere to percolate down to. That doesn't make any sense. I promise. It'll work out mathematically in a couple slides. So the first round of percolate downs does nothing. It's like those things, they don't have anywhere to go. Great. We've already made our way to the middle of the array. Now I'm going to look at 9. Do I need to percolate down for that? No, it has nowhere to go. Great. 2, does it need to percolate down? No, it's greater than 6. 10, does it need to percolate down? Ah, finally, we have our final percolation, our first percolation. We do our one swap there, and then we leave it, and we move on, and 3 doesn't percolate. Then we come to 11. 11 is going to do a percolate down, and then it needs to percolate down one more level, and then we come over, and we come to 5. We have a percolate down there, whoopsies, and one more there. Great, now 3 is in its spot. And then finally, we have a percolate down of 12, and it's got to go the length of the tree, so on and so forth. Now, the reason we do percolate downs is because statistically, the majority of the nodes in this tree sit closer to the bottom. There's just more nodes at the bottom of the tree than there are at the top of the tree. So statistically, we have fewer things that need to travel up than down. So I am more likely to have those like, great, I don't need to move kind of moments if I'm always asking myself, do I need to move down? In fact, there are a bunch of terrifying math slides in here from when I used to make you do proofs to show you that if you amortize the analysis across all of this, if you think about the statistical likeliness that you're going to have to percolate down the number of nodes at each individual level, it all ends up rounding out, there we go, to run in O of n time. And it's just about how many nodes need to actually travel the full height of the tree. So Floyd's build heaps algorithm, which says add everything all at once and then call percolate down starting from the back of the tree forward, will actually run, instead of running in n log n time, which would happen if you ran insert n times, it actually amortizes overall to run in just linear time, to insert everything into the heap and maintain it in the structured way that it is. I don't care if you understand the math of it, but you should just know that we get linear group insertion. I think that's, there we go. Any questions about Floyd's build heap? I can't remember if I asked you to implement build heap or not, honestly. Cool. Okay. All right. There we go. Cool. Yes, there are a few other operations that you may encounter increase or decrease priority. You are going to have to do that. We talked about that a little bit. There we go. I think that might be sweet. Great. Okay, honestly, that is all I actually have for today, and thank goodness, because I am ill. But I am happy to answer any other questions that everybody has, but otherwise, I say we end lecture early so that I can rest. Let me know if you have any questions. Yeah, what can I do for you? Yes, the midterm's in this room. Yes, be here Friday. Thank you. Cool. Oh, hang on.
So we're going to start handing them out. Do not open the test. You can put your name and email address on the top. But as you come in, we're going to hand you a copy of the test. Please do not open it and just put your name on it. We'll get started when everyone gets settled.